Good morning. Next we will see what is Poisson's equation. Okay. So till now electric field intensity was determined using Coulomb's law or Gauss law when charge distribution is known, or by using E equals minus del V when the potential V is known throughout the region. But in practical situations, neither the charge distribution nor the potential distribution will be known. Okay, that is in these three cases, that is in Coulomb's law, Gauss law, and using the formula E equal to minus del V, you should be having some knowledge of the charge distribution, or either you should be having some knowledge of V inside the surface. Okay, but practically it is not possible. That is, if you are not having any knowledge of the charge distribution inside the surface, or if you are not having any knowledge of V, that is potential, inside the surface, then how will you calculate your electric field intensity? There comes the importance of Poisson's equation or Laplace equation. In this equation, how they are calculating this E is, you will be having some knowledge of the charge and potential across the boundary of that surface. Okay, across the boundary. And using that knowledge, you will be calculating the electric field intensity. That is why Poisson's equation or Laplace equation is known as boundary value problem. Clear? So from Gauss law, del dot D equals rho V, and we know D is equal to epsilon E. I am substituting 2 in 1. So I can write del dot epsilon E is equal to rho V. Again I know E is equal to minus del V. I am substituting 4 in 3. So I can write del dot minus epsilon del V equal to rho V. Then this del and del multiply gives del square V, and minus epsilon is taken separately. So I can write minus epsilon del square V is equal to rho V. So that del square V is equal to minus rho V by epsilon, where rho V is my volume charge density. And this is the Poisson's equation. Now if your region is free of charge, okay, the region you are going to study is free of charge, then this rho V will be equal to 0. Then I can write del square V is equal to 0, which is your Laplace equation. So here you can see Laplace equation is a special case of Poisson equation for a free charge region, rho V equal to 0. As I said earlier, if your region which you want to study, the region you are taking to make a study is free of charge carriers, then that region will not be having any volume. So rho V will be 0, and finally this becomes del square V is equal to 0. Okay. Now this is a procedure for solving Poisson's or Laplace equation. It's enough to go through this. Okay, it's not that much important. So first what you have to do is, first you have to see whether that particular region has charge or not. If it is a charged region, then you can use Poisson's equation, and if it is a free charge region, then you can use a Laplace equation. Okay. Solve Poisson's equation if rho V is not equal to 0, or Laplace equation if rho V is equal to 0. Next you have to apply the boundary condition. So you will be taking a region and you will take the data which is available from the boundary of that region, and using that data you will find out V. Once you find out V, you can find E. What is E? E is equal to minus del V. Similarly, if you know E, you can find D. D is equal to epsilon E. D is electric flux density. Here there is a slight mistake. It is not magnetic flux density, it is electric flux density. Okay, please correct it. Then the current density also can be found out using the formula J is equal to sigma E. Okay, J is equal to sigma E. So in short, the point you have to keep in mind is you have to use Poisson's equation or Laplace equation if you are not having any knowledge about the inner space of your surface. That means you doesn't know anything what is happening inside the inner section of your surface. You don't have any idea of your charge distribution, you don't have any idea of your V, that is your potential within that surface. Okay. In that case you will go for Poisson's or Laplace equation. There what you will do, you will try to get the data from the boundary of that surface, not inside the surface, from the boundary of that surface, and using that data you will find out E, V, etc. Is it clear? That's all related to Poisson's and Laplace equation. Next we will see some application of our potential. This has nothing to do with Laplace or Poisson's equation. Okay. First we will see the potential due to a hollow sphere or a shell. Okay. As we learned earlier, a hollow sphere, inside the hollow sphere there will be no charge distribution. It will be hollow. So the charges will be seen across the surface. Okay. Now this is the center point of my sphere. Okay, this one center. Actually this point is exactly the symmetric point of this one. Okay, this one. Okay, so now I am assuming that here the calculation is initially done on the assumption that the charge is placed at the center of the Q. You should never misunderstand that inside the sphere there is a charge. Actually, whenever I say that there is a charge inside the center, you should keep in mind that that center is here. Okay, that center is here. Whenever I say that in this particular application the charge is placed at the center of the sphere, then you should keep in mind that center of the sphere is this point. Okay, this point, not the one inside the sphere. Okay, now the charge Q is placed at a distance small r from point P. So the electric first case is P is a point outside the shell. Shell is a hollow sphere. E is equal to 1 by 4 pi epsilon 0 Q by r square. We know V is equal to minus integral E dl. But here instead of dl you have to write dr because I have taken the distance as r. So I am writing the expression as dv is equal to minus E dr. Okay. Then simply I am substituting equation 1 in 2. Then I can write dv is equal to minus 1 by 4 pi epsilon 0 q r square dr. Then if I have to find v, I have to integrate. Finally I will get q by 4 pi epsilon 0 1 by r, which is the potential at my point V outside the hollow sphere, that is V out is equal to Q by 4 pi epsilon 0 R. Now here it is written, this derivation is done on the assumption that charges are placed at the center of the hollow sphere. Okay, potential at P1 will be equal to potential at P. As I said earlier that whenever I say that the charge is placed at the center of the hollow sphere, then you have to keep in mind that this is not the center point. Actually this is the center point of the sphere. So okay, so if the potential at P due to this Q is q by 4 pi epsilon 0 r. Then the potential at P1 due to the charge placed at this point will also be what? Q by 4 pi epsilon 0 r. Okay, V out is equal to Q by 4 pi epsilon 0 r. In case 2, we have to find the potential if P is on the surface of the shell. Okay, that is here if P is on the surface of the shell, then you know the radius of the sphere is r, right? Radius of the sphere is r. Okay, radius of the sphere is r. Then what will be the equation for V? V is equal to 1 by 4 pi epsilon 0 q by capital R. And since it is at the surface, I am writing it as Vs is equal to 1 by 4 pi epsilon 0 q by capital R. Next, what I am going to do is, when P is inside the shell, we know inside the hollow sphere or shell there is no charge, hence electric field is 0. Clear? So dV is equal to E dr. E inside is equal to 0, that is this value is 0, so I can write dV is equal to 0. Now in order to find the value of V, what I am going to do is I am integrating this. So dV, integral dV is equal to integral 0. So I can write V inside is equal to a constant, right? When you integrate dV, you have to integrate 0 also. So finally you will get V inside is equal to a constant. So if I differentiate this equation, what will I get? dV is equal to a 0, right? So I can write V inside is equal to a constant. Then what will be that constant value? V inside എന്ന് പറയുന്നത് it is a constant. അപ്പോൾ constant എന്ന് പറയുന്നതും അതിനും ഒരു value ഉണ്ട്. So what will be that value? That value V inside is equal to your Vs, that is equal to 1 by 4 pi epsilon 0 q by capital R. Okay, that constant value of V inside is Vs, your Vs, which is equal to 1 by 4 pi epsilon 0 q by capital R. Clear? And this is a graph showing your variation between Vs and R, that is inside the shell it is will be like this, and after that it will slowly start decreasing. That means you know the V is inversely proportional to R. So as R increases, your V will decrease. Okay, as V will decrease. So inside this much you have inside shell, you are having a particular value, and here it will be maximum, then it will slowly come decreasing. That's all.